This is Angela Galloway from Math 146, and this is a lecture for 12.4. So this is still Unit 4, Section 4 of Chapter 12. So 12.4, we're covering measures of position. So what we've done so far is we looked at measures of central tendency and then measures of dispersion, right? So we looked at, the mean, median, mode for central tendency. For dispersion, we looked at the range and the standard deviation. And now for measures of position, we're looking at where our data falls in our distribution, okay? So one of the problems is when we talked about outliers, we figured out how to identify outliers with a mean and a standard deviation, right? If we have the mean and we add and subtract 3 standard deviations, if we have an observation that falls outside of that range, then we consider that an outlier, okay? Or a special result, something that's really high or really low, something that was unexpected. However, remember we talked about back in back in section 2, when we were looking at central tendency, we had 2 measures of center, right? We had the mean and then we had the median. If we had a skewed distribution, we didn't want to use the mean because it was skewed by the outliers, right? So if we know that we possibly have outliers or we've got a skewed distribution, then really we don't want to use the mean to describe, our distribution, right? We instead want to use the median. But if I use the median, can I use the standard deviation? Can I do the median plus or minus 3 times the standard deviation to figure out an outlier? Well, not really, because how do we calculate the standard deviation? We use the mean, right? So if the mean is skewed by outliers, the standard deviation is as well, because the mean is in the formula for the standard deviation. So if we can't use the mean, then we can't use the standard deviation. So we've got the median that we can use, but we need something else to describe the rest of the distribution besides just looking at where the middle is, okay? So this is mainly for data that's not symmetric, okay? If it is symmetric, you're probably going to use the mean and the standard deviation and then the empirical rule to describe things about your data. If it's not, then we can use what we're going to call the 5-number summary, but basically using the median, okay? So before we get into that 5-number summary, we have to look at some terms. So the first one is percentiles. Percentiles divide data sets into 100 equal parts. A data set has 99 percentiles, notated P sub k for the kth percentile. So for example, if you had P sub 5, that would be the 5th percentile. If you're in the 5th percentile, that means 5% of people are below you, 95% are above you, okay? So you've probably ran into percentiles before. Maybe you took the ACT or the SAT and afterwards they showed you where your percentile was. Maybe you scored in the 80th percentile. So that means 80% of test grades were below yours, 20% were above yours, right? Or maybe you have kids and you've taken them to the doctor and they've looked at the height or weight charts and they tell you that your kid is in the 30th percentile for height. Well, what does that mean? Well, that means that 30% of kids are shorter than them and 70% of kids are taller than them, right? So that's what percentiles mean. So we're pretty familiar with percentiles. Another thing, though, that we use a lot in statistics is quartiles, okay? Quartiles actually are special percentile. They just divide the data into 4 equal parts, okay? So the first quartile would actually be the 25th percentile, okay? So the first quartile divides the bottom 25, so it would be this yellow part here, from the top 75, okay? Q2 divides the bottom 50 from the upper 50, and we know that is called the median, right? The median falls right in the middle. It separates the bottom 50 from the upper 50. So Q2 is actually the median, so we just call it the median instead of calling it Q2. Q3 is the third quartile, so it divides the bottom 75 from the upper 25. So those are what we are going to use to help describe our data. So to kind of see how our data is distributed in a distribution. Okay, so let's do an example of that. Okay, this one is looking at TV viewing times. Okay, and so this is a sample of 20 people and their weekly TV viewing times. Okay, then it says determine and interpret the quartiles for these data or for this set of data. All right, so looking at this, the first thing we need to do with this data set is find the median. Okay, so if you're finding the quartiles and you're doing this by hand, which you may or may not do, because we'll show how to do it on our calculator too. But if you're doing it by hand, first what you want to do is arrange the data from smallest to largest. So if it's not already like that, make sure you arrange it from smallest to largest, because remember with calculating the median, it's looking at the position a number is in, right, where it is on the number line. So if you don't have things in order, then that's going to mess up your calculations, okay? So we arrange the data from smallest to largest here. That's why I have the data rewritten. Then we want to find the median. Okay, so remember, to find the median, we can use this n plus 1 over 2 formula to help us find which observation is the median. We have 20 data points here, so 20 plus 1 over 2 is 10.5. That tells us to take the 10th and the 11th observation and divide by 2. So the middle of this data set here is right here, okay, right in between 30 and 31. So our median is going to be 30.5. So we add these two, divide by 2, that gives us the middle. That's our median. Now that we've found the median, okay, of the entire data set of numbers, we're going to split the data into two sets of numbers, the lower half of numbers and the upper half. Okay, so this red part over here is my lower half of numbers. The blue part is the upper half. Okay, to find Q1 and Q3, we really just do this process over again, calculating the median, but we do it for the lower half of numbers and the upper half of numbers, okay? Q1 is actually the median of the lower half of numbers, okay? Because when I find Q1, I'm separating the lower 25 from the upper 25 in the lower half of numbers, right? So I'm splitting this 50% in half, okay? So really I'm just finding the median again, okay? But just for this red set of numbers. So now for my lower half, I have n equal to 10, right? So to find the middle of that, that would be between the 5th and the 6th observation. So we get 21 plus 25 over 2, and that gives us 23. So that's our Q1. Q3 is the median of the upper half of numbers. So we do the same process again. Again, this side also has n equal to 10. They're both going to be the same size because we split the data in half with the median, right? So we get 35 plus 38 over 2 gives us 36.5, and that would be our Q3. So these would be our quartiles, 23, 30.5, and 36.5. Okay, and then just as a side note, if you happen to be calculating quartiles by hand and your data set has an odd number of observations, what happens is when you do that, this would be our median, right? 5 falls right in the middle. Well, once you calculate the median and then you're trying to separate your lower half and your upper half of numbers, sometimes students can get confused with that. Because here, when we calculated the median, it was in between these two numbers. So it was easy to see that that separated the lower half from the upper half, right? Because this just cut it right down the middle. This one though, do we let 5 be with the lower half or the upper half? Do we get rid of it? Do we put it in both the lower and the upper half? How do we deal with that? And so the way your book decides to deal with that, and most books decide to do with that, is just to ignore the median and then let this be your lower half of numbers, this be your upper half. Okay, so when you're separating the data, you find the median, then you kind of exclude it, then look at the lower half of numbers and upper half. Once you have this, then you would find this would be Q1, this is going to be Q3, right? Because they're in the middle of their data sets. Now, if you're doing this in your calculator, you don't really have to worry too much about it because it's going to, calculate what you need. You don't have to worry about if there's an odd or even number of observations. But just if you're doing this by hand, you might want to note that there that you need to ignore the median if you have an odd number of data points. Okay, so now that we have determined what Q3 and Q1 are, we're going to use them to be able to identify outliers. Okay, so what we're trying to get to is these lower and upper fences or lower and upper boundaries. And what those do, those are going to be our cutoff points to determine if we have an outlier or not. Okay, so in this lower fence and upper fence here, if we have anything that falls below this number, okay, then it's going to be considered an outlier. So this is our lower fence or our lower boundary. Okay, then we have an upper boundary, which is our upper fence here, the Q3 plus 1.5 times the interquartile range. If anything falls above that, then it's an outlier. Okay, so we have these boundaries here where we say most of our data is going to fall. If we have anything that falls below here or above here, then we say those are outliers. Okay, so what is this IQR here? The IQR is the interquartile range. The interquartile range is Q3 minus Q1. Okay, so once we find Q1 and Q3, we can plug that in here, get our interquartile range, plug it into this formula, and get our lower and our upper fences. Okay, the next important thing is the 5-number summary. The 5-number summary is just a grouping of numbers we've already figured out how to calculate, but it's putting them all together at once. And what that does is give us a quick view of what the data looks like, okay? A quick summary of the lowest and the highest numbers, and then how the data is spread out in between those, okay? So we start with the minimum. You want to put these in order. They should increase as you go to the next number. Each one should get bigger. So the minimum comes first, so you know where your data starts. Then you've got Q1, then your median, then Q3, and then the maximum, so you know where your data ends. So like here, just going the min and the max, you can find the range. The Q1 and Q3, that gives you the interquartile range, which is our middle 50% of the data. The median separates the lower 50 from the upper 50, so you could use that to calculate things or whatever. Okay, so going back to the example we just did about TV viewing times, this is our 5-number summary. 5, 23, 30 and a half, 36 and a half, and 66. Okay, so what we would want to know is, looking at each of these differences here, each of these represents 25% of the data, right? 25% of the data falls here, 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 and here. So if you notice that one space looks like a larger range of numbers than another, that might clue you in that there's some skewness happening there, or that there's an outlier there or inside of there somewhere. So like we're looking at, is 5 an outlier? Well, let's look at our data. Does 5, it goes from 5 and then to 15. Is 5 far enough away from 15 to be considered an outlier? What about 66? It's pretty far away from 44. Is that an outlier? Is that an extremely high TV viewing time or not? Okay, so that's what we're trying to decide is, are those extreme observations, or are they just high or low observations? And the way we can figure that out is by using these lower and upper fences. So let's plug in all our numbers from our last problem and see what these lower and upper limits or fences are going to be. So our lower fence here is going to be 23 minus 1.5 times 13.5. So it's always going to be 1.5. That's just in the problem. So you're always going to use that. You're just going to plug in your Q1 and your interquartile range. So here we get 2.75. So that tells us anything below 2.75 is an outlier. So did we have any numbers below 2.75 in our data? No, right? 5 was the lowest. So in this, based on this data, 5 is actually not an outlier, right? Because it falls inside of those lower and upper fences. Now the upper limit is 56.75. Okay, so do we have any numbers that fall outside of 56.75? And we do, right? 66 falls up here, so it would be considered an outlier. Okay, so that was an extremely high television viewing time compared to all the other ones. Okay, another way we can find outliers without having to calculate those lower and upper fences is by using our calculator, because our calculator can calculate it for us. Okay, so we can use box plots in our calculator to show us if there's an outlier or not. We can also use these box plots to show us the shape of the distribution. Okay, so what are box plots? Box plots are really just a graphical representation of the 5-number summary. Okay, so in general, the box plot shows all 5 numbers of the 5-number summary. So you start with the minimum value, then you have Q1, your median, then Q3, and then your maximum. Okay, so you've got these 5 points. Then around Q1 and Q3, so your middle 50% of the data, you make a box. The median gets a line drawn through it. And then you extend the tails out to the minimum and the maximum value. Okay, and that is how you get your box plot. Okay, so you probably aren't going to be constructing box plots much in your homework. What you'll be doing more of is just identifying or reading those box plots. Like if I gave you this box plot and it had numbers below it, let's say it had these numbers. Okay, so down here we're on a number line. Okay, so let's say I asked you to tell me what the median was. Well, you would have to know that this line represents the median, and that line is at 7, so the median is 7. Q1 is 5, Q3 is 9. Okay, so that's how you could read the box plot without actually having to construct it. So you might just be reading one or matching one to your data to show which one correctly shows your 5-number summary. Now, something else special that we can see with our box plot, like in our calculator, is we can choose one of the box plots and it will show us if there is an outlier. If it has a star or a dot on your box plot, then that identifies a possible outlier. Okay, so what it does is if the minimum or the maximum or one of the values extends past the upper and lower limits or fences that we just calculated here, then it replaces that minimum or maximum with the fence and calls the other observation an outlier. Okay, so let's look at how to do that in our calculator. Okay, and so this is a pretty neat feature to do. So what we're going to do here is first we've got to put our data in, right? So we go back to stat and edit, just like we did for our one variable stats. If you still have data in here that you want to get rid of, go up here and push clear. So go up to the list, highlight it, and push clear and enter. And then all your data will be gone there. Now I'm going to go back to this data set that we were working with because we want to be able to see the box plot show us that outlier. Okay, so here's all my data here. You can type in your data in order if you want, or just up here, it doesn't matter. So I'm going to type in all my data. That's what's going to take the longest here. So let me type that in, and you can be typing it in at the same time if you want. Let me make sure I didn't make any weird mistakes there. Okay, everything looks good. So there's my data in L1. Now that I have my data in there, I'm going to go to second and y equals because I want to get to the stat plot area there. Okay, I'm going to go to the first one and just push enter. Okay, the first thing I want to do is turn this stat plot on. If I don't have it on, then it won't show my graph. Okay, so let me go back down here to where our instructions are in case you're reading that at the same time. Okay, so now we're here at step 3. We went to stat plot and turned it on. Now you notice that there's all these different graphs here, okay? This first graph is a scatter plot if you wanted to do that, and we'll do that with linear regression in the last section in chapter 12. You can do a histogram. This is something we won't use. That's normal probability plots. These two you can tell are box plots, right? So why do we have 2 box plots? Well, the first one here, let me get my cursor off of it so you can see it. The first one here that has the dots tells you that it's going to identify if there's any outliers in your data. Okay, so we want to use this one if we're trying to find if we have outliers. Okay, if you just want to see the shape of the distribution, so if you want to be able to tell if it's skewed or symmetric or whatever, you could use this second one. This one does not account for outliers. So if you have a number that's really extreme and it's an outlier, it's still just going to show it as the minimum number or the maximum. So you would get something that looked more like these where it shows the skewness of your distribution. And so that second one is good if you're trying to show if you have a skewed or symmetric distribution. The first one is good if you're trying to actually identify the outliers. Okay, so when I go down here, I'm going to arrow over. So I'm arrowing over, do the over button, to this first one with the dots. Okay, and I'm going to push enter. Once I do that, it's going to ask me where my data is. Mine is in L1, so I do second one. If yours is in another one, just do whichever list yours is. Okay, uh, we don't have a frequency list, so just leave that at 1. This is the mark that it's going to use to identify an outlier. So that's just something, just your own personal preference. I always just use whatever is marked there. That's just fine for me. All right, the next thing we're going to do, we're all ready. We make sure you have it turned on and then go to graph so you can see it. Okay, now if yours looks like this, we just need to adjust the zoom. Okay, so we need to adjust what we're seeing because all we're seeing is one tail. We're not seeing the rest of the box plot. So we're going to go to zoom. And then number 9 in Zoom, you can either push number 9 or arrow down to it. Number 9 is called Zoom Stat. That is going to zoom or rezoom your window around whatever stat plot you have turned on. So that's what we want to use for this one. So push enter. And then we get to see this, right? So now we see that box plot there, and we can see that there's an outlier. But if I don't want to go back and look at the original data and figure out what that outlier is, I can go to trace and notice that it goes onto the graph and it tells me what each of these points are, right? So it says the minimum is 5, Q1 is 23, that's my median, there's my Q3. This is actually just going to be my upper limit, okay, where I figured out, what's going to be an outlier or not. And then my maximum value there, which is 66, which also happens to be an outlier. Okay, so you can also use this box plot feature to figure out your 5-number summary if you wanted to. That'll give you your 5-number summary. The other place we found the 5-number summary is if you do the 1-variable stats, right? So if I do 1-variable stats, so I go to stat, calculate, and do the 1-variable stats like we did before. My data is in L1 again. Just push enter. The 5-number summary is you have to arrow down here, and these 5 numbers is the 5-number summary. So if you just need that for a problem, you could do it that way, or you could do it by actually doing the box plot and finding your 5-number summary that way by doing the box plot in the stat plot and then doing the trace and just, arrowing to the right and getting all those numbers. Okay? So there's a lot we can do with our calculator here. If you want to do it in Excel, if I wanted to find the 5-number summary, you notice that over here this is what we did with the descriptive statistics in our data analysis, it doesn't have the 5-number summary there, right? It does have the median, and it has the minimum and the maximum, but it doesn't have Q1 and Q3. So how do we get that? Well, we do equals, right? That's how we get it to start our equation that we're trying to solve. And we just type in quartile. Okay, I'm going to do quartile and then parenthesis. It says it wants the data. Array is just where is your data. I'm going to highlight that. And then comma, and then whichever quartile I want. And it even tells you how to do it, okay, as you're typing in. So if I want the first quartile, I can either double click this or I can just put a 1 there. That means I want the first quartile. Okay, if I want the third quartile, then I do quartile, I highlight my data and do comma 3. Okay, so that's how you can get the quartiles using your Excel. If you want to find the minimum and the maximum and the median, you can do it all at once, doing it this way, or you can type in, the minimum there and highlight this, the maximum, which I think we've already done this before. You have to do equals, the maximum. And then remember that the median is just the second quartile, right? So if we did the second quartile here, that would give us the median, the same thing that we got there. So those would be our 5 numbers. Now they're out of order, but remember you always do smallest to largest. So it would start here, then we'd have, that's our minimum. Then we have Q1, then Q2 here, Q3, and then that's our maximum. So when you write out your 5-number summary, it should always be from smallest to largest. Okay, so we're almost at the end of 12.4. The last concept here is also helping us to determine where our observation falls in the distribution, okay? And that is using the standardized variable, which is also called the Z-score. That's usually what I call it. What the Z-score tells us is how many standard deviations our observation is from the mean. Okay, so if we get a positive Z-score, that tells us that our observation is above the mean. If we get a negative Z-score, that tells us that our observation is below the mean. Okay, so that's what our Z-score is telling us. If I get a Z-score of 1.5, it tells me that my observation is 1.5 standard deviations above the mean. Okay, so what we can use the Z-scores for is we can use it to tell just where our observation falls in the data set, or we could use it to compare different data sets, and that's what we'll do in the next example. For the first example, though, we're just going to calculate a Z-score. So let's say we have a distribution with a mean of 9 and a standard deviation of 2. What is the Z-score of an observation of 13? Okay, so we have something that looks like this. Okay, we have the 9 is in the middle, the standard deviation is 2. Now, where does my 13 fall? Okay, it falls above the mean, right? So I should be getting a positive Z-score here because I'm going above the mean, right? So Z equals X minus mu over sigma. That is our Z-score formula. Okay, so again, remember, you don't have to worry about memorizing formulas, but this one you'll probably kind of have memorized because you'll use it a lot. But Z equals X minus mu over sigma. So we plug in our numbers, 13 minus 9 over 2, and we get 2. So that tells me that 13 is 2 standard deviations above the mean. Now, what about 5? What about the Z-score of 5? What would I get? Well, I plug in a 5. I get 5 minus 9 over 2. That gives me a negative 2. So that tells me that 5 is 2 standard deviations below the mean. Okay, so a negative number, a negative Z-score just tells you that your observation fell below the mean. Okay? Now let's look at using z-scores to compare distributions. Jenny scored 600 on the verbal part of the SAT. Her friend Mike scored 21 on the verbal part of the ACT. Who scored better relative to their test? Okay, so if we weren't able to convert these to z-scores or percentiles or something like that, we would be unable to compare these scores, right? Because Jenny scored 600, Mike scored 21. So does that mean Jenny did better because 600 is bigger than 21? Well, not necessarily, right? Because the SAT and the ACT have totally different scoring rules, right? So we have to find a way to be able to standardize our scores. That's why it's called the standard score. Or the z-score. We have to find a way to standardize those scores so that then we could compare them to each other. Okay, so the way we're going to do that is we're going to look at each of the observations, compare them to their distribution's mean and standard deviation, and see how far away they were, how many standard deviations they were from the mean. And if we compare those two marks, then we can tell if one is better than the other. Okay, so for Jenny's z-score, we get a z equal to 1. Mike's is a z equal to 0.5. So since Jenny had a higher z-score, that means she scored higher in her distribution than Mike did. So Jenny would be the winner and have the highest score. Okay, another important thing that z-scores can tell us is, since they're telling us how many standard deviations away our observation is from the mean, they can describe outliers for us, right? If we have a z-score of 3 or greater, or -3 or less, then that tells us that our observation is more than 3 standard deviations from the mean, right? And that is what we identified as an outlier. So be on the lookout for those when you have really large z-scores. Then it's possible that you have an outlier because it's more than 3 standard deviations away. Okay, so that's another way we can use the z-score. Okay, so that's the end of 12.4. If you have any questions, be sure to email me at angela.galloway@kctcs.edu.